Today we are going to see some examples of the use of the root locus method, and this way we're going to practice on how we enter a transfer function in MATLAB and how do we obtain the root locus plot, and also how do we actually use the position of the poles and the zeros to understand a little better what the system is doing. So that's the objective of what we're going to do now. So on the screen, I have a very basic loop of a system and a feedback, and we are going to take a look on how you can see on the transfer function of the system, we're going to call it G of S, and the control, or again, in this case, a proportional control here, simple system. We're going to call it K, and then this is the feedback loop. But let me disappear from here. We are going to see how we put this to first in theory and then in practice. And okay, so you have in here, as you see, you have in here on this an open loop system, because this is the input, this is the output. However, if we measure the output, as you see over here, and then we put it through a transfer function of its own, we can compare to some reference point in here of what we want to do. Like, for example, if we are setting the temperature, if this is a room in here, if this is the temperature of a room is what we are doing. This is our room, and then we would have in here a reference point on which we will a reference point about which we measure things. So if we have the output over here and we compare it to the input, the difference is basically an error that we see over here. That error is what is fed to the controller, and that output is fed to the system. That's how we do a new comparison, a new feedback, and this thing goes on like this. So what we need to do is to obtain a standard form of the transfer function. So we could say that the output that you see in here is first of all, let's put here, let's call it error. I'm going to write the letter E for error here. Yeah. So in this case, this output, we could say, let's see if we can write it down here. The output of this is equal this error. All right. This error of S multiplied by K, and then multiply by G of S. Yeah. And then we can say that the reference, which is your input, some reference of S, minus the output of S multiplied by H of S. This is equal to this error. Let me stop for a second and review this so that everybody is with me. So in here you see you have the excuse me. you have, this is the output that you see here is the input, which is error multiplied by k multiplied by g of s. That's what I wrote on the first equation here. And then we have this reference here minus obviously the output of s multiplied by the h. That is going to be our error. So let's see, we had a little bit of an issue here. Let's see if we can fix it. How do we get it back? That's one first challenge that we have right now. So I believe that was on the draw. We did something with the eraser, so well, we may have to do it again in the interest of time. But I thought that the undo button would actually bring it back. But all right, let's try it again. What I was saying is that the output of this one, it's a good practice, is equal to the error of s multiplied by k, then multiplied by g of s. I also said that the reference minus the output of s multiplied by h of s, this is the error of s. Okay? If we want to have a relationship between this point that is the input and the output, see, if we want that relationship, then we have to eliminate this error of s and put it into this equation. So what I would do is we say output of s is equal to the error of s, which was r of s, minus output of s times h of s. Yeah. And then this, I would put it like this, times k times g of s. So now we just have to play with algebra a little bit, and you'll see what we get. So this would be r of s times k times g of s is equal to, no, equal, minus, excuse me, this was output of s like this, minus output of s times h of s times k times g of s. And you may say, where are we going? We are going in to establish a transfer function between this reference and then the output. That's what we want. That's what we want. A reference between this and this. This is what we want. Okay? So in here we need to play with it to put all the terms that contain the output on the other side. And so I would say output of s plus, bring this to the other side, output of s times h of s times k times g of s equals to what? Is equals to r of s, right? Times k times g of s. Okay, very good. Remember what we want. We want the output over the input. So we want out over R of S like this. This is equal to, we will have up here K times G of S divided, this would be over 1 plus K times G of S times H of S. And this thing, once we have done this, what has happened here is that we have reduced the system to a transfer function of the closed loop system, where this is R of S in here, this is the output, and in here this is K G over 1 plus GH. See? So this is the closed loop transfer function. Okay, so let's just do an example right now. Just go over here and do an example in here. And say that the transfer function here is this transfer function output of S over R of S like this is equal to, I'm going to write the polynomial that this is S squared minus 4 S plus 20, and the transfer function over here of the system is going to be expressed in factors, like this. And then, see? Okay, so the question here is what the root locus plot is going to do is going to take the closed loop transfer function. Where is the, I just moved it a little bit in here, and part of it disappears, so let's put it back. This was K times G of S, right? So this thing is the closed loop transfer function. So if we give the system a transfer function like the one we have right now, like this, okay, we could ask the system to study what happens to the roots if we change this K. So we could give the values of K equal to 1 all the way to K equals infinity, and see and study what happens, what is the change. So the first thing we're going to do is to enter this into MATLAB, and then ask MATLAB to do our root locus. And so here is MATLAB, and I am going to first of all, we're going to type clear so that we have all variables free, and I am going to say the numerator of the, let's call it GH so that we know it's a closed loop transfer function, is going to be a polynomial that has a 1, and then it has a -4, and then it has a 20 here. And then we are going to say return. So I got the numerator as a polynomial, but the second one is in factors. So I am going to say the denominator of the transfer function is we're going to say this is a polynomial of factors whose roots are, like in this case, -2, right? And the other root is going to be a -4. And then this is, does everybody see why I'm saying roots -2 and -4? Let me just bring it back. See here? If you set this to 0, s equals -2 and s equals -4 are the roots. So we specify it that way. And what MATLAB does is also converts it into a polynomial in here. And then what I am going to do is to say, I'm going to define the transfer function, let's call it G1, equals the transfer function between the numerator of GH and the denominator of GH. So right now, this is the transfer function we are working with. Okay? It's a continuous time transfer function. Now, after this, we want to study the root locus, which I already have explained, and through the other video, you know what the concept of the root locus is. Given this transfer function, we are going to change the value of k from 0 to infinity, so that we can do this. So the root locus, the root locus is going to be of this transfer function, right? So if I do this, I immediately get a figure. I'm going to get a plot in a moment of what this is. There we go. Now let's see how we're going to read this, because that is important here. You see, what this is trying to say is, okay, hold on for a second. What this is saying is the numerator, the roots of the denominator are called zeros, remember? So let me just put it there. There you can see, here's the transfer function, and this is the plot. See, the roots of the zeros of the numerator are these ones. And the roots of the denominator are obviously that -4 and -2, you see? So if you change, you start over here. You basically start over here. But if you change the gain, you change the k, what's going to happen is the poles are, the zeros are going to come this way, like that, and the roots are going to go this way. See? So you have a simultaneous plotting of where the zeros go as a function of the value k. I believe that we need to study this in a little bit more detail, more in depth, and use some of the MATLAB tools to be able to study this. Perhaps just to remind you, this is the imaginary axis, this is the real axis. Let's see if we can actually get this so that I am able to write on it. Okay, there we go. Yeah, now I'll be able to write. So these are the zeros here, and these are the poles. See, so this come from the numerator, and this guys come from the denominator. What I was trying to tell you is this, the value of k equals to 1, then this is the zeros start over here, and as k increases, they're going to go this way, like that, see? So this will go like this. And then the plot will go this way and this way. But I believe it is important to use some of the MATLAB tools to be able to understand a little better this. Like if you have a root here and you draw a line from here to the origin, it's a little bit crooked, but it's supposed to be a straight line. Now let's just do a little better job, okay? So that way, okay. This is the natural frequency of the system. Remember, this is the imaginary part. This is the real part. So this goes like this, and then see. Okay. So we need some tool that would allow us to examine what the plot actually means. So what we're going to do is we're going to go back to MATLAB over here, and we're going to say, okay, let's define some damping ratio and the natural frequency, and put a grid over it, a grid over that plot that we just have. So we're gonna, bear with me for a second, we're gonna define these parameters here in steps of 0.2. And then 0.2 to 0.5 is what we want. Okay, this is like a damping ratio of 0.2, and then we're gonna say column, so it indicates the step 0.05, and then column to 0.5 like this, and then column, so that defines a range of values that we want. The natural frequency, we're going to establish again a range from 0 in steps of 1, let's say, until 10, like that. And then we're going to say, let's put the grid is on the grid. Let's grid. We're going to put it on the plotting here using Z and omega n. And you'll see what that is going to do to our plot over here. So let's just see. I wanted to show it at the same time, but see what it did? It put a grid on the plot we already had for the damping ratio values from 0.2 to 0.5, and they gave us an idea of with for each damping ratio what the value of the value of the root should be there. So in here, let's see, we have the we would like to define the okay, so we have the root locus over there. Let's see if we do a close-up of this and we define the axis. We could do that, but I think that maybe this is enough. I think we could see it in there. But what I want to do is I want to show you a very neat command so that you can actually make good use of this plot that you have on the right. Let's see if I can reduce the MATLAB window a little and keep this one over here. This is the command that would allow us to do an examination, you may say, of the values of k and look at the variations. So if we use the cursor on the screen as to how this would look and what the values would be, root log find numerator of GH and the denominator of GH, like this. I think you're gonna like this. We'll see. You see now, this has changed. It's really nice how this works, because in here you could go to any value of the on this. You could go to a value on the plot and find out what the selected point values are. Hold on for a second in here. Okay, I'm gonna get back over here. See here, you could click anywhere over here and it will tell you the value of the gain. So let's say you pick a damping ratio of 0.5 over here and you click over here. You see what happened? It give you the roots, those two roots in here, and on the left it told you what they are. These are the values of the roots. These are the poles, and this is the gain k. So if you want to see, for example, what's the crossover frequency, what's the crossover point over here, all you have to do over here is do it this and then activate it again, and it's going to tell you the point where this is the maximum gain that you can have, so that the system does not become unstable. See, this was before 0.037, 1.5, and the system becomes unstable if you go to the right side. In fact, if you apply the same method, you see how the roots are here because of the imprecision of the mouse zero. I could put a 0, 0 and then have only this, but the 0.048, which is a very small amount. But now I'm going to go the other way around. I let the computer do this, and then I'm going to select the point over here. See what this is telling you? It marks it on the root locus, but it's telling you it's 0.6 positive, then plus or minus 4 point. So it's positive this way and plus or minus the other way. So you know that's the point where the system is unstable on the right hand side, just so that I remind you of the for a second order system what the expected reaction is going to be. So let's just do this so that we can actually write on it. Yeah, see, there it is. So what I'm trying to say is, where's my pen? What I'm trying to tell you is that what this is saying is that the system over here, well, let's draw first this one. This one over here is something like this. But this one on the right hand side, it starts like this and it would blow up. So not good here. And the system like this is totally, vibrates like that forever. But this one like this would actually dump like that. These are the kind of things you need to know, how the poles get affected by the change of the gain, which is a great piece of information that the root locus gives us. Okay, so let's stop now here.